Hello everyone, hope you all are doing well, taking care of yourself as well as your family. Uh, this is our first lecture on the course title Fluid Mechanics 2, and in this lecture we are going to start fluid flow around submerged bodies, and we are going to cover those topics: submerged bodies introduction and their example, and with some basics which is required to learn this particular topic. Before proceeding, we should know what is exactly the meaning of submerged body. If I'm considering an ship here, and if I'm consider water as a fluid, in that case this ship cannot said to be a submerged body. Instead, I will say it is an example of floating body. Although it is submerged in the air and air is also a fluid, but I am considering water as a fluid here, and in that case this will be treated as a floating body. So, whatever the submarine which is totally sinking in the water or used to move through the deep sea water can be an example of submerged body. So, submerged body is that body which is totally surrounded by the fluid which you are going to consider. So the ship can be said to be an submerged example of submerged body if I am considering air as an fluid. So if I am considering air as an fluid, we all are an example of submerged body because we used to live in atmosphere and atmosphere is filled with the air. So we all are surrounded by the air and we all are an example of submerged body. You can also take an example of building as well. So whenever any object which is come in contact with the fluid, at that time they will be subjected to certain amount of force which will be exerted by the liquid or that flowing fluid. So whatever that magnitude of those force which is exerted by the liquid as a fluid resistance will depend on the condition whether my body is moving or fluid is moving or whether both are moving with the certain velocities. But this force will be exist there because of velocity difference in between object and fluid. If I am considering a case where my submarine and water both are moving in the same direction, so let us consider both are moving in this direction with the same velocity. In that case, there will be no force exerted on each other. Whether a body is not going to exert any force or fluid is also not going to exert on the body. But if I am considering a case where my submarine is moving with a certain velocity and fluid is moving with the different velocity, in that case due to the concept of relative velocity or due to the velocity difference, this body will subject it to certain amount of force which will be exerted by the fluid. So we are going to consider all those cases. So our case number one, my body will be at rest condition and fluid is flowing with a certain velocity. In the second case, fluid will be at rest condition and body is moving with a certain velocity through the static fluid. And in the third case, both body as well as fluid are moving with the certain velocities. We will discuss those cases one by one. So in the first case, my body is at rest condition and fluid is flowing with a certain velocity. You can take an example of this bridge where the bridge is stationary and this liquid is flowing over it with a certain velocity. In this case, my fluid is going to exert certain amount of force on this particular bridge, and according to Newton's second law, body is also going to exert equal and opposite force on the fluid. You can also take an example of this building where those buildings are surrounded by the air and will be subjected to certain amount of force which will be exerted by the air, and this force will be there because of velocity difference between object and fluid. In the second case, my fluid is at rest condition and body is moving with the certain velocity. You can take an example of this diver, or you can also take an example of this submarine which is moving through the static water, as those submarines are used to move through the deep ocean water where water is generally considered as static. So in that case also my fluid is going to exert certain amount of force on the body as a fluid resistance. Remember, in both the cases, whether my body is moving or fluid is moving with the certain velocities, magnitude of the force is going to remain same. And in the third case, both body as well as fluid are moving with the certain velocities. In that case also, if the velocity difference is there, if there is a relative velocity, in that case also fluid is going to exert certain amount of force on the body. You can take an example of vehicle which is moving on the road. It will be subjected to resistance provided by the air. You can also take an example of sky jumper which is falling down. You can also take an example of aeroplane which is moving in the air, which will be subjected to certain amount of force or resistance provided by the air. Let's talk about the basic which is required to learn this particular unit. We will start with the Reynolds number. As we all know, Reynolds number is the ratio of inertia force to the viscous force. And so if I am going to write the equation for Reynolds number for the pipe flow, so I can write it as rho Vd upon mu, where rho is the density, V is the velocity, D is the diameter of pipe, and mu is the viscosity. As I can see here, this Reynolds number is going to will be directly proportional to the density, velocity, and diameter, and will be inversely proportional to the viscosity. So as my viscosity increases, Reynolds number decreases. As my density, velocity, and diameter increases, Reynolds number also going to increase. So we use Reynolds number to classify whether flow is laminar, whether it is turbulent, or whether it is transitional. Again, if I am considering the a plate, Reynolds number for the plate, in that case equation of the Reynolds number will be modified as rho u L upon mu, where L is the length of plate. And if I am considering length of plate as infinite, in that case Reynolds number equation will be modified as rho u x upon mu. Next basic is the boundary layer. So we all know, whenever my fluid come in contact with the solid boundary, or whenever any object or any obstruction is come in the flowing fluid, at that time there will be a development of boundary layer exactly near to the boundary, due to the development of no slip condition because of adhesive forces of the liquid. So if I am considering an here boundary, and if this boundary is at rest condition, at that time whatever the liquid which is come in contact with this boundary will attain whatever that velocity having this particular boundary. So if the velocity of this boundary is 0, at that time the layer exactly near to this particular boundary will attain that same velocity due to the adhesive forces. And when my layer 1 is coming in contact with that particular boundary, it will attain the 0 velocity. And when my another layer coming over the layer 1, that is layer 2, in that case layer 1 is going to provide resistance to the layer 2. Now this will be there because of concept of viscosity. As we all know, viscosity is the resistance provided by one layer of fluid to the another adjacent layer to flow over each other. So whenever my layer 2 is come, at that time layer 1 is going to provide resistance to the layer 2. Now in the initial stage, my layer 2 will overcome on that particular resistance, but soon after it will lose its all momentum whatever it have previously, and after that its velocity will be decreases. Again layer 3 will come, and again layer 3 will also try to overcome that resistance, but soon after, when it loses its momentum, and when it don't have enough momentum to overcome that resistance, its velocity will also decrease. Same thing will happen to the layer 4. At the initial stage it will overcome the resistance, and soon after that when it will become unable to overcome that resistance, its velocity decrease. Same thing will happen to layer 4, layer 5, layer 6, and so on. Accordingly, this whatever my velocity is going to affect, and there will be a development of velocity gradient. So whatever the velocity having layer 1 will be the whatever the velocity having that boundary, but whatever the layer 2 will have certain velocity. If I go to the layer 3, it will have certain more velocity than the layer 2. Layer 4 again, it will have more velocity than the layer 3, and this same thing will happen and goes on up to the all layers of the fluid. And according to and this, in the same way, our boundary layer thickness will goes on developing in the downward direction. As I'm moving in the downward direction, in this direction, so my thickness of the boundary layer will goes on increases, and the boundary layer is that region in which velocity gradient will be exist. If I'm coming out from this particular region beyond this boundary layer, there will be a velocity which will be equal to the free stream velocity, or whatever the velocity before to the obstruction or before to the boundary. So here I can see that development of boundary layer thickness. Next concept is the dimensional analysis. As we all know, dimensional analysis is the mathematical technique which we are generally using to solve many engineering problem by using some fundamental quantities. So we all know we are generally make use of those 4 fundamental quantities, and we used to write down all the equation in terms of those quantities which are generally known as secondary quantities. So our primary quantities are mass, length, time, and theta. So this dimension analysis is generally based on principle of dimensional homogeneity, and in which we are going to make use of primary quantities or fundamental quantities. So we all know, if I am considering an equation of discharge which is given by area multiplied by velocity, and if I want to write it down in terms of dimensions, so I can replace this area with the length multiplied by length, that is length square, and this velocity, which is unit, is meter per second. So meter is the again length, and second is the time. So I'm writing all those terms in the form of primary or fundamental quantities, and I'm converting its expression in the fundamental quantities, and this L cube T inverse can be known as secondary quantity or derived quantity. So for the dimensional analysis, we generally make use of principle of homogeneity. So principle of homogeneity states that if I am considering any equation, the dimension of each term of the that particular equation, if both dimension on the both side of that particular equation is the same, then that equation is said to be a dimensionally homogeneous. So if I'm considering an example here, v is equal to under root of twice of gh, equation of theoretical velocity, and if I put the units on the both side, and if I write down the quantities of those units, so here it is meter per second on the left hand side, and on the right hand side unit of this g is meter per second square, and height is the m meter. So I'm going to write down it in terms of primary quantities, that is meter per second, can be written as L divided by T, that is LT inverse, under root of, here again meter per second square can be written as length multiplied by T raised to minus 2, and meter again length, so here it is L square under root of L square divided by T square. So I can take the square root, and in that case if you see here, my units or quantities on both sides are coming same. LT inverse is equal to LT inverse. So this equation can be said to be a dimensionally homogeneous and consistent in unit. So this equation, you can use this equation in any a unit system, like say SI unit system or MKS unit system. We generally make use of relay method. Most commonly used method for the dimensional analysis are relay method and Buckingham pi theorem. There are many others, but we are going to discuss only those two, and we will solve one numerical on the basis of relay method. So here it is, we are going to work out the dimensional analysis, how you can solve the problem by using dimensional analysis. So here the problem is given, the time period t of the pendulum depends upon the length L of the pendulum and acceleration due to gravity, that is g, and derive an expression for the time period. So in the dimensional analysis, first we need to write down the equation in the form of functional relationship. So I can write down the equation for this t here, t is equal to function of this particular L and G. So I'm going to replace this relationship of function as a with a constant k, which is dimensional quantity, dimensionless quantity and constant. I'm going to replace that k for the functional relationship. So I can write down this equation first as t is equal to t is the function of L and G. After that, I'm replacing that f with the k, which is dimensionless quantity and constant. Now after that, I'm going to write down that equation in the form of this constant as t is equal to k, L and G, and after that I'm going to install arbitrary constant, arbitrary power, arbitrary constant as a power, a and b both are arbitrary constant, and after that I'm going to put the dimension on both sides. So dimension of t, time is the t as its unit is second, again k is the dimensionless, no need to put anything for the k, and again here is the L length, dimension of length is L, again G, its unit is meter per second, so I can write down for meter length, and for the second time raised to my 2 times square. So here it is, dimension for the G is LT raised to minus 2, again B is the power. Now I am going to compare those power on both sides for the M, L and T. So here there is no M in the expression, so whatever the power of m on the both side will be null. Again I am going to compare the power of L on both side. So here it is power of power of t on the both side. So here power of t on the both side, here it is 1, on the right hand side it is minus 2b. So I will get the value of b is equal to minus 1 by 2. Again for the power of L, I am going to compare power on both side. So on the left hand side there is no L exists, so power of the L will be 0, and the right hand side here power of L is a, and here it is power of L is b, so a plus b. So I'm going to replace the value of b with the 1 minus 1 by 2, minus minus will get plus, I will get the value of a as a 1 by 2. So I'm going to substitute those value in this particular first equation where I have written the equation for the t. So here it is t is equal to k, L raised to 1 by 2, G raised to minus 1 by 2. So I can write down it in equation form as t is equal to k under root of L divided by G, and you can find the constant value of k experimentally, and it can be found as 2 pi. So equation for the t can be written as t is equal to 2 pi under root of Lg. So this is what we use dimensional analysis to find the relationship between different variables. Remember this thing and go through some numerical. I will give you some assignment to solve it at home. to solve those two numericals at home, because those are very important whenever we are going to discuss about the some derivations for the drag force and lift force. At that time we are going to make use of those two problems, so I am not going to teach this separately. You need to solve it by using Rayleigh's method. Whatever the method we have just used, just make use of that method. You can also use the Buckingham pi theorem and just solve those two numerical, and we will continue with the uh, submerged bodies in the next unit, next lecture.